All right, let's get started. Make sure I have all this information where I need it. All right, so last time we talked about matrices, where we said we defined here's what a matrix is. We talked about like the inverse, how to write something, how to multiply two matrices, getting the product, how to add them, all that fun stuff. So that's sort of serves as one of our prerequisite sections. We're doing another one of those for the next couple classes. And so we're going to start by talking about propositions. And the key question with propositions is, how do we make a logical statement? So we want to be able to say something and say that that thing is either true or false. And so we define that as a proposition. So a proposition, also known as a statement, in mathematics is a declarative sentence that is either true or false. And so when we say the statement is either true or false, whether it's true or false, like the actual which one it is, not whether, that's not the right word. Maybe the choice, true or false, is the truth value. So I have a statement, and the statement is my iPad is connected to the projector. That statement is true, so its truth value is true. The statement, I'm using whiteboard markers right now, is it is a proposition, it is a statement, it is false. The truth value is false because I'm not using whiteboard markers right now. If the statement is ambiguous or something is undefined, then it's not a proposition. So this textbook is the best. That is a declarative sentence, but I don't know that I can assess the truth value of that sentence. We need some more rigorous metrics. Like, what are the reviews? What do people say about the book? Maybe we say like it has 5 stars on Amazon. That's a declarative sentence, and that truth value can be either true or false. Either it has 5 stars on Amazon or it doesn't. But saying like this textbook is the best is not clear, so it can't be a proposition. Okay, so I've got practice in the handout. And let me pull that up just so you've got that on the screen. If I can struggle my way over there. Nope, I've lost it. Like stuck between the two screens. No. Okay. So this is the propositions document. And so let's just look at the first part of that. And so talk with your neighbor. For each item, I want to know, is it a proposition? Yes or no? And if it is a proposition, decide its truth value. Is it true or false? And then once you get through all of those, then look at the ones that aren't a proposition and see what changes could you make to make it a proposition. Maybe there's no changes, but for some of them, there are a few. Okay, go for it. Talk with your neighbor. All right. What's number one? Is it a proposition?
Yes.
What's the truth value? What about number two? Is it a proposition? Could we make a change to make it a proposition?
Yes.
It is raining. Yeah. And if we did that, what's the truth value? False, unless you count fog as rain. So maybe it's still a little bit ambiguous for our context. Maybe like there is currently precipitation, something like that. What about number three? Is it a proposition? What's the truth values? Great job. Number four. Is it a proposition? What change could we make to make it a proposition? Well, I bought tickets to the concert. I am buying tickets to the concert, something like that, that makes it either true or false. This, how do we pronounce this? 12 divides 6. Left divides right. A divides B. Is it true? Correct. It's false because 6 divides 12. 6 times 2 equals 12. 12 does not divide 6. There's no number we can multiply 12 by. There's no integer we can multiply 12 by to get 6. Yeah, keyword integer. What about 7? Is it a proposition?
No.
Yeah, why not? Yeah, it's ambiguous. Why is it ambiguous?
I mean, it's not like clear, like number 3 is a very swift negative integer such that it's 3x.
Right. Yeah, and so we have no idea what x or y is. And so we're missing that context. And so if we added in context where maybe like we defined one of the variables or we defined both of them, then that's a statement that we can then say is either true or false. What about 11? Is 11 a proposition? No, why not? Yeah, it's ambiguous. The book has an example of like if you look at a specific test and Georg performs better on that test than Leonard, then we can say that that's a true statement. But as is, it's too overly broad. How do we quantify that? So we can't be able to say that it's true or false. Great. All right, so it's fairly easy to define a simple proposition, right? You just have to write something that's either going to be true or false. The next bit here is like these are statements that seem fairly easy to see. Like understanding the definition is easy. I wish I could zoom in more, but I can't. Can I? I can. So yeah, so understanding these definitions may be easy, but deciding or proving whether it's true or false is hard. So maybe talk about these. I'll give you 3 minutes maybe to think, are these true or false? Sometimes they're unknown, sometimes they're undecidable. So think about it for a second. Talk with your neighbor. Go. Okay. Any ideas? Any ones that we think are clearly true or false? Yeah,
I think two is clearly false.
two is clearly false. Okay.
There's no false, I don't know if they want to do anything in the market.
Um, so the book says this is true.
They want to be unique integers then?
Given any collection of 16 integers, I think unique may be inferred
Okay.
with what we're about to talk about regarding sets. But that is an interesting point where if you just take non-unique integers, then it's false.
Yeah.
Any other ideas for these 5 problems? Yeah.
I'd say, 4 is definitely true.
Mm-hmm.
There's also an infinite amount of numbers. So in that case, it's also going to be like an infinite amount of prime numbers that are one more than square of an integer.
Mm-hmm. So yeah, so here's where we kind of get into the fun stuff where let's see. So 1 is true, 2 is true, 3 is false, 4 is question mark, 5 is true question mark. Where even in mathematics, there are some problems where we're like, for number 5, we're like, this is probably true, but we don't know how to prove it yet. So number 5 is something called Goldbach's conjecture, which is a conjecture is something that we think is true, but we haven't proved it yet. And so they're like, if you solve that, then you get a prize and like instant PhD. Number 4 is it's not, I don't know that it's named after anybody, but it's also, we don't know if that one's true. So there's fairly, we can break these down into simple propositions where we've got infinitely prime numbers, and the special case is that they're more than one more than the square of an integer, which seems simple to understand, but very, very difficult to prove. So don't be fooled by easy statements. Sometimes they are easy, sometimes they're not. We can, there we go. We can write propositions. We'll see this on Wednesday, where if we write a proposition like with the lowercase letter p, and we can define the statement, so like it is raining, or Earth is a planet. So just to sort of introduce you to the notation that we'll be using next time. And so we'll use this to build up to more complicated notation. All right, so that's our talk about propositions. That's 3.1. Now let's talk about sets. So the book doesn't define sets very rigorously. I don't know that anyone really does. We kind of are building our foundation on vibes of here's what a set is, and then we kind of just go forward with that. Because the book says, interestingly, though, the term set itself is a primary notion of mathematics, and we do not define it. However, a set is basically a collection of objects. where we're using such broad language that, I don't know, that doesn't really mean anything. And similarly, we'll define an element as one of those objects. What do I have in my notes? An individual object in a set, right? So a set is some collection of objects. An element is an individual object that's in that set. Sets are really abstract. So I could have a set of like the 50 states. That's a collection of objects. Um, is it something that I can see right now? No, but I know like there's 50 states. I know we can have a set of the letters of the alphabet, A through Z. We can have a set of everyone in the world who was born in January, or everyone who has ever lived who was born in January. That's a collection of objects, of people. I don't know who all of those are. Let's see. We could have all even integers. That's a set that's infinite. It goes on forever. Or all prime numbers. Similarly infinite. So it's abstract, it can be vague, but in general, it's a collection of objects. It can be anything. They don't even have to be related. So I can have my calculator back in my office, this classroom, like the physical room, and my friend's puppy. Those three things form a set. It's a collection of objects. However, we try to define sets in mathematics that have things of all the same types. So that's kind of like when you use Python, you can have a list of anything, but we tried to say that everything in the set's going to be the same type. So that's going from like Python lists to Java arrays, where we say everything has to be its own type. So we'll talk about definitions. So try to keep same type, I'll say. Okay, so in terms of how we write a set, we write it with curly brackets. So they will be very bad to start with, and then as you keep practicing, you get better at it. I have maybe like 10 years or so of practice, and so mine are decent looking. They were not to start with, I promise you. So we write it with curly brackets. And so let's say we have a list of numbers, a list of integers. So let's say A is 1, 2, 3, 4, 5. I denote it with curly brackets, and then I separate the things with commas. So this should look familiar if you remember lists and arrays. It's just that we use curly brackets to say this is a set. We usually name a set with uppercase letters, especially if we're just usually just one uppercase letter. But again, it kind of depends. It's just a variable name, so it can be whatever we want. Convention is uppercase. And then the elements, if we have some set A, we try and use like the lowercase letter that goes with it. So like the elements of matrices. So let's talk about inclusion. So if A is, again, let's say 1, 2, 3, and 4 this time. So that's my set. My set contains 1, 2, 3, and 4. I can say 1 is an element of A. And so we say that some elements, let's call it A. So if A is an element of A. Remember, element is just an individual object in that set. So if A is an element of A, we write A and then this weird epsilon E looking thing. And then the name of the set. And so this is read A is an element of the set A, or A is in the set A, or A belongs to the set A, or the set A contains the element little a, right? All equivalent ways of saying the same thing, just trying to get our language standardized. And so I think I mentioned this before. When we are writing this in LaTeX, which we will get to very soon, we'll use the \n to write this thing. So it's not quite an epsilon. And then, so we can say that the number 1 is in A. We can say that the number 3 is in A. What about the number 5? Is 5 an element of A? No, it's not listed there. And so the way we say that is we write that and then we draw a line through it. And so in LaTeX, we could do not in, or they've got a shorthand not in, all one word. Right. And so then when we say this, it's basically all of those statements, except we say 5 is not an element of A. 5 is not in A. 5 does not belong. So we just negate that statement. All right, so let's say, so we should talk about repetition, which kind of gets to what you were suggesting earlier with all 16 integers being the same thing. When we're talking about a set, A being 1, 2, 3, 4 is the same thing as us saying if we've got so many ones in that set, it's the same set. So let's say the duplicates are ignored and don't really matter. So we only count unique elements of the set. If we write it with 10 ones, 10 twos, 10 threes, 10 fours, that's the same set as 1, 2, 3, 4. So duplicates are ignored. They don't matter when we write sets. We say that a set is finite. This is probably a duh statement where it's finite if it has distinct elements. So you had a question. Wait, what's my, nope, hold on. Let me get that right. Finite if it contains finitely many elements. What was your question?
How would you do order, like for the set? Like where would you put the position if there's like multiple duplicates, not in one spot? Like there, all the ones are in one line, but if they were throughout the set.
Order also doesn't matter. Equals 4, 3, 2, 2, 1. Order doesn't matter in a set. Duplicates are treated like they don't exist. Other questions? Yeah, or no? That's a question. Great. Okay, so it's finite if it contains finitely many elements, which is kind of self-explanatory. This is important because otherwise we call it infinite. And so this is like the difference between the integers from 1 to 10 versus all positive integers, right? In one of them, it's finite. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In the other, it's infinite, all positive integers. So that's finite, that's infinite. We can talk about the cardinality of a set, also known as the size, because we like to make up words for things. And so the cardinality is the number of distinct elements in a finite set, right? So for the numbers 1 through 10, the cardinality is 10 because I've got 10 integers. The cardinality of all positive integers is undefined because the set's not finite, and I don't know how many positive integers there are. I can't put a number on that. So let's say actually, let's look at our old use of A. What's the cardinality of A? 4. Even that set? Yeah. So there's 4 things in A. So cardinality of A is 4. Let's see. What about, let's say B is 2, 5, 6, 10, and 4. The way we write it is with those are the pipe characters. Again, it's just above the return key on your keyboard. And so when you're typing it in LaTeX, that has to be in math mode. But we write it as it's like the absolute value of a set. And so we say the cardinality of A. What's the cardinality of this set B that I've got here?
No.
0.
Sorry. Oops.
Yeah, 5. Yeah. What about that's supposed to be a curly bracket. See, I'm still not good at writing curly brackets. What's the cardinality of C here? 2. Why not 3? Because there's 2 of them, and we ignore duplicates. All right, so when we're working with super large sets, so ordinarily, like if we've got small enough sets, we can just write it out of, here's my set B, here's all the numbers in B. That's fine. So we can write it, separate it out with commas, and that's all fine and dandy. But if we're working with a large set, then we want to use what we call set builder notation. And so the idea here is we want to provide a rule to be able to obtain all the elements of the set. So we don't necessarily want to list them all. We just want to say, here's how you would get all of them. And so let's see an example. So we'll use A again. And we write set builder notation where we have the curly brackets. And then we have some sort of, we've got two parts to it. So you'll see it's either broken down with the pipe character or a colon. Either works. When I first learned this, I used the pipe character, so that's what you'll see. I think the book uses the colon. It's equivalent. And so we have a notion of some sort of general statements on the left-hand side, and on the right-hand side, we have some sort of restriction. So the left-hand side is more general, the right-hand side is a restriction. So let's say we want to use set builder notation to describe all the even numbers. So we want to describe all even numbers. Well, all even numbers is broad. There's a lot of different kinds of numbers. What sort of numbers are we probably thinking about specifically? Integers. So yeah, so the book, and then maybe we want to further restrict it of, do we want to include negative numbers? Do we want to include only positive numbers? So we have to think, like, to be able to restrict this down into something very formulaic that we can write in set builder notation. So the book looks at only positive integers. So that's like 0. Well, since we're looking at evens, so they're looking to, let me rewrite this. They're looking to have 2, 4, 6, 8, and so on. We could write this in a set notation with the dots, but maybe we want to specify what exactly the dots mean. So we're going to write that as A is equal to curly brackets. And so now we're going to have our general formula, which is where we're going to say some variable lowercase n is going to be in the natural numbers. So remember that fancy Blackboard n is natural numbers. But that's our general statement. But we're going to further restrict it by saying n is even. There's a lot of different ways I could have written this right-hand side. I could have said n mod 2 equals 0, n is divisible by 2, so we could say like 2 divides n, we could have said as well. There's a lot of different ways we can express this stuff. And so you can use words in set builder notation. So like n is even, those are words that we write. So the key is to practice being concise and specific to get us what we want. Okay. Do I have that written out? I don't think so. All right, so let's open up to the textbook. I will put it up on the screen. And I'm going to look at page 35. And we'll look at no, let's not do this again. Okay, so we're gonna look at example 13. So turn to your neighbor and we want to see, so we're starting with some set S that has 5 elements. Notice that we also allow a set to contain sets. So that's interesting. Take a few minutes and wait, hold on. No, I missed stuff. My bad. I gotta talk about more stuff before we get there. I skipped a step in my notes. That's my bad, sorry. So yeah, so sets can contain other sets. We could have 2, 4, 3, 6, 6, 8. That's a set. It's kind of confusing, but that's technically allowed. Remember, it's just a collection of objects. If we have a set that has nothing in it, so set with nothing, then we have, then we call that the empty set. And so we write that as like a 0 with a line through it. In LaTeX, that's \empty set. And this is just saying the set with no elements. You'll also somewhere see it called the null set. Null meaning nothing, again containing nothing. Sometimes it's also written just empty curly brackets. And so let's see, so this set, the empty curly brackets, is equivalent to saying I'm going to have integers such that that integer is between 0 and 1, non-inclusive. There's no integers that are between 0 and 1. So there's nothing in this set. This is like saying a proposition, and then this must be false because there's no integers that will satisfy that. It's like saying that I want a rational number such that x squared is equal to 2. The square root of 2 is irrational. So there's no rational number that's going to fulfill this requirement. So the set is empty. This is also equivalent to saying I'm going to have a real number such that x squared plus 1 is equal to 0. Basically saying that x has to be equal to the square root of -1, which is undefined for the real numbers. So these are impossible statements, meaning that the set, there's no numbers that satisfy those requirements. So then the sets must be empty. All right, a few more definitions, and then we've got time to work on problems. So we've got subsets, which are, we say that A is a subset of B, so 2 sets, and we denote it A and then this C, this long C looking thing with a line under it. I'll write it a few times so you kind of get the idea of what it looks like. And we write A subset B if all elements of A are in B. So if A is 1, 2, 3, and B is the numbers 1 through 10, then all the things in A, 1, 2, and 3 are also in the set of numbers 1 through 10. And so we write A as a subset of B. This can also be reversed. So if I want to have B on the left-hand side, I can draw the symbol the other way. And this reads B is a superset of A, so subset and superset. This tends to be super confusing, so if that's confusing, don't worry about it. But just know that we can write it the other way. There's just a different term for it. But this is still saying if we read right to left, that still reads that A is a subset of B. What happens if this is true? If A is a subset of B and B is a subset of A? Yeah, the same set. So all the things in A are in B. All the things in B are in A. That means they've got to be the same. So they've got to have all the same elements. So then we say A equals B. And so that's fairly self-explanatory. Otherwise, if they're not equal, we write it with equal sign with a slash through it, which is NEQ in LaTeX. Or not, and then equal sign. Then we've got the notion of a proper subset, where we can say, so like if I have two sets that are the same, I can clearly write one is a subset of the other. That's fine. It's trivially a subset of the other, but 1 through 10 is a subset of 1 through 10. If I have 1 through 9, let's say A is 1 to 9 and B is 1 through 10. I can write it like this, like A is a subset of B, but maybe I want to say that they're not equal to specify that. So if one is a subset of the other, but they're not equal, we can write it as A subset B. And so there's a few symbols that can help. So this is just that same symbol without the bottom line. That's kind of equivalent to less than or equal to. Like 3 is less than or equal to 5. It's not equal, but saying that it's less than or equal to 5 is also technically true. But we can be more specific if we want to say that 3 is less than 5. The book doesn't have it, but there's also a symbol where you can have that bottom line with the slash through it to say that it's subset, but it's definitely not equal. So that's another option for you. And so writing this notation, that is what we call a proper subset. So if A is a proper subset of B, they are subsets, but they're not equal. And then we say if A is not, hold on. And then we can say if A is not a proper subset of B, then we write that proper subset symbol, excuse me, and just put a slash through it. And so that's equivalent if we have A is 1 through 5, B is 6 through 10. They're both sets of numbers, but A is not a subset of B, and so we would write A, not a subset B. You could also add the line here because that it's like the way the command for that is subset EQ, EQ for equals. This is just subset. I don't remember the command for that one. I'm sure it is similarly. Wait, hold on. Let's find it. Let me show you this awesome website. So there's a website called Detechify, which is super useful when you're starting to learn LaTeX and you want to know what's that symbol. So if I draw it with my trackpad, and I draw a slash through it. N subset EQ. So I'll make sure you have access to this on Canvas. It's just a website that you can use to, okay, let's see. That's a subset NEQ. So yeah, so there's a lot of different options. Okay, now I think I've properly gotten to the end of my notes. So we've got some time. Let's go back to, did I move where did Canvas go? There it is. So we've got a spare few minutes. So first talk with your neighbor. Do you think the empty set is a subset of every set? And then I've got these, which is technically one of your homework problems. So we've got 3 minutes to talk about it. Go for it.